Hello everyone. Welcome to the second weekly live session for the course Earth Sciences for Civil Engineering. A brief introduction for anybody who is new today. Myself, Ananya Mukherjee. I am a fourth year PhD student in the Department of Earth Sciences, IIT Kanpur, and I'm also the recipient of the Prime Minister Research Fellowship, PMRF. So these weekly sessions that we are taking for the NPTEL courses is actually one of the deliverables that we have to fulfill for the PMRF duties. So hopefully these will, serve as an extra, resource for you to understand the course and also get your doubts solved about the weekly, the course lectures or the assignments that you are given and also help you learn a bit more. And we also have to take this because we are fulfilling this duty towards the PMRF. So, hoping that you all will join every week at 6 o'clock and we can conduct these successfully. So, I will start with today's session then now. So, a brief, is my slide visible? Am I audible? Just put it in the chat box.
Yes, ma'am. You are
Okay.
audible.
Okay, great. Okay, so a quick overview of what has been given for your second week, the lecture content is that you are introduced to the mineralogy aspect of earth sciences, geology. So in that we understand what minerals are, how minerals and mineraloids are different, and fuel minerals also. Minerals are inorganic in nature and they occur as aggregates of different crystals of a particular structure. Mineraloids are also minerals, but the form of theirs is not exactly in a crystal. You cannot see the crystal structure very clearly. So these are called mineraloids. And then you have fuel minerals, which are actually organic in nature. Okay, like petroleum, natural gas, coal, but we still call them as fuel minerals because they're naturally occurring. Okay, so all the minerals have a different mode of formation. There are three major modes of formation.
Ma'am, your voice is breaking.
Is it audible now? Properly?
No, ma'am.
Hello,
Uh,
it's clear now?
yes, ma'am. Now
Okay.
you are audible.
Okay, so there are three modes of occurrence. One is when the magma, it's after it's extruded from the Earth's surface and it cools down, or it's also beneath the Earth's surface and it's cooling down. So the cooling of magma is one of the ways that you find minerals, how minerals crystallize. The second is the secondary processes. Now, secondary processes means pre-existing minerals and rocks are present. They either get chemically dissolved and then precipitated out, or due to weathering and erosion, they start disintegrating and converting into different crystals of different chemical composition. So that's how secondary minerals are also form. And the third way that minerals form is due to metamorphism. Metamorphism is pre-existing rocks, they undergo kind of different thermal metamorphism or regional metamorphism, and the minerals actually change in their composition or in their crystal structure. So these are three ways where different kinds of minerals are formed. So then they are accordingly they are also put into different categories. So the next very important thing that has been introduced to you is the crystal structure. Then you have mineral classification based on the formation processes. The silicate minerals are classified as per their silicate structure. Then the temperature, crystal symmetry. We'll touch upon these even in today's session, and we'll try to understand, how to. There are examples for it, so I'll try to explain those examples also. And then you have mineral identification in hand specimens, and there are few physical properties that we look at, we try to understand when we are trying to, identify the minerals. Now, minerals identification is necessary because that kind of shows the stability of the rock. The strength of the rock is also determined and influenced by the presence of these minerals, and that is how you can deduce whether that rock is suitable for civil engineering purposes or not. So this is one of the most important aspects of mineral identification, where civil engineering is considered. And then you have the different rock types. So the rock types that has been taught to you in the in the second week is igneous rocks and introduction to sedimentary rocks. Igneous rocks also we classify as per the magma origin, their mode of occurrence, and the mineral composition that the rock is associated with. Then you have different identification properties. You have rock texture, then the rate of cooling, and color index, and also it is also based on the mineral composition that is there in the rocks. And the sedimentary rocks are also again classified on the basis of their modes of formation, mineral constituents, and origin. And then you have types of sedimentary rocks, that is also you identify as per the sediment type, grain size, grain roundedness, and grain sorting. I will show the examples of all of these rocks and how you can understand what exactly like what kind of sorting is present, how the grains actually look, whether they are rounded or subangular. So, moving on, these are the crystal systems that we learn. Now, crystal systems is actually, as you can see, there are faces. The crystal faces, they join together to form a proper a crystal over here. Okay. So, the first one is the cubic system. The second one is tetragonal. The third one is hexagonal, and hexagonal also has another kind of system under it that is called trigonal. Then you have orthorhombic, then you have monoclinic, and then you have triclinic. So the only differences in all these is either the length of the axis or the angles that are made by the axis. So in cubic, you have all perpendicular to each other and all are equal in length. In tetragonal, one of the axes, usually the vertical one, is longer in length. And in hexagonal, you have two more faces. You have six-faced crystal, and it has six axes. There are three horizontal and one vertical. In orthorhombic, all three are perpendicular to each other, but the lengths of all the axes are different. In monoclinic, one of the axis is inclined. Okay, one of the axis, and all the axes are mostly usually of different lengths. And in triclinic, the axes are not at all perpendicular to each other, and they all have different lengths. Okay, so the first column that you see here, these are the normal class of these. So you have system, you have class, and then you have forms. So each of these are different forms, and each of these form different classes. We are not going to get into the depth of this because that is currently not required, but we have to remember these seven systems that we are that has been taught to you in during this week. Next, one of the important thing is crystal habit. Now, crystal habit is actually the shape. It's the aggregate that you see. Uh, just wait. Okay. So the aggregate of all the crystals. Suppose you have a lot of cubic crystals, okay, and they are accumulated together and entirely they are forming a mineral. Okay, a mineral is present with all the different cubic crystals. Now, when you look at it, the One particular crystal is cubic in nature, but when you look at it, you will find that it looks granular. It looks like, there are small, small grains of these crystals. That is called a habit. Okay, so now a habit can be of different kinds, like over here is mentioned bladed, cubic, fibrous, granular, prismatic, radiating, nodular. Okay, now cubic, when we say, actually it's supposed to be tabular. When we say tabular, that like many crystals come together to form the mineral, and the mineral, looks like a block. That is kind of a tabular habit of that mineral. Okay, so now we have rock forming minerals. So these minerals are categorized into two groups. One is silicate minerals and one is non-silicate minerals. Silicate minerals are also then again classified into different groups. You have quartz, feldspar. Feldspar is also potash feldspars and plagioclase feldspar. These are two different groups. Then you have mica, amphibole, pyroxene, olivine group, garnet group, clay minerals. Okay, now these silicate minerals, each of these have a different kind of silicate structures also. Over here to the right, you can see the figure. So the first one is called neosilicate or the tetrahedra. This is the basic tetrahedra of the silicon dioxide. So this is actually the olivine. Olivine group of minerals are formed with this crystal structure. Then you have sorosilicate, that is two tetrahedra are joined. Then you have ring silicate structure. Okay, so this forms a ring. So lot of hexagonal crystal system minerals, they form this silicate structure, like beryl. Beryl is one example. Okay, then you have a single chain of say of the tetrahedra joined together, and then you also have a double chain. Okay, so these are called inosilicates. One is single chain inosilicates, and this is the double chain inosilicates. Now, the single chain inosilicates, you will find example in amphibole, I think. Yes, amphibole, and the double you will find in pyroxene. Okay. Then you have sheet silicates, where there is these silicate structures. Usually, the crystal structures are, they form sheets of different crystals. Okay, when you even see them in hand specimen, they form flaky kind of minerals. Like you can pick up one sheet and you can take it out. And then the last one is framework silicate. This is SiO2. This is the very commonly known quartz, is one of the minerals which crystallize in this silicate structure. Then you have non-silicate minerals. So non-silicate minerals are oxides, sulfides, sulfates, carbonates, phosphates. Usually, most of these minerals are found in sedimentary rocks. There are few oxides which are found in your igneous rocks and metamorphic rocks also. We'll see that later on. So now we have the Bowen's reaction series. Now the Bowen's reaction series explains how minerals crystallize from the molten magma. Okay, so when we are saying that the olivine is crystallizing first, okay, that means actually these have very high melting points. Okay, these crystallize out first, that means these have very high melting points. So, uh, when as we know that magma is it's coming uh, on top from the mantle, it's moving on top. Okay, so the temperature also is starting to cool down as and when it is reaching the surface. Okay, so according to that, these minerals crystallize one after one other. Okay, and according to the composition of a combination of the mineral composition, we kind of categorize the rocks as per that. Okay, so this is the entire this is how Bowen's reaction series is understood with respect to the formation of different minerals and rocks. we can see the quartz is the last to crystallize. So this means that if a rock starts melting, okay, this is when we are talking that it's cooling and forming the mineral. Suppose there is a rock which contains quartz and it is melting. So the first thing that will melt, the first mineral that will melt is quartz. So this is how we understand this diagram. Okay. So now we come to mineral classification and identification. So can you see the mineral over here, the mineral which is in the black background? Okay. So can someone just look at it and try to guess which crystal system will it be? Like cubic, tetragonal, hexagonal, orthorhombic, monoclinic, or triclinic? Some anybody just put it in the chat box, or you can unmute yourself and answer. It's okay you if you don't understand, you're not understand. I'm hoping that you will understand with this. So anybody? Okay, so we'll start with the most basic. Can you tell me which color the left figure, the mineral is the color? This is the color. You can use the chat box and give the answer. There's no issue. Just say the color that you can see.
Brownish color.
Okay, so we can go for like a grayish, peachish color. Okay, and the one next to it is what? Just the basic color of it. Okay, so I'll just type it out. We are calling it pink for now. Okay. Now, what is the luster? Luster is the way light is reflected off a mineral. Okay. So we have different luster, that is vitreous, that it looks like glass. Adamantine, that it is very sparkly like a diamond. Then you have pearly. It has a very a sheen to the surface. Then, so these are some of the lusters that are there. So I'll just give for this mineral for now. So the luster for this mineral would be vitreous. Okay, as you can see in the pink one. Okay, the pink one. In a hand specimen, you will see that the light is reflected off it, like how light reflects from the glass. Okay, so the luster is vitreous for this mineral. So, and streak is the third identification property. Streak is necessary because sometimes the mineral color is not exposed, or the mineral color might be showing a certain color, but the streak will have a different color. Okay, so the streak is actually very important when it comes to softer minerals, because you can see anything that is very hard, the mineral will not show a streak. A streak is made when you rub the mineral on a tile, a porcelain tile. Okay, so for orthoclase, for this mineral, sorry, the mineral there you will have kind of a white streak. Okay, then the hardness of the mineral is 6. So, as I had asked before, can you say what crystal system this looks like? You can see that one axis is tilted. Okay, so when one axis is tilted, which crystal system will you call it then? So, it is a monoclinic crystal structure. Okay, And the mineral group is feldspar, and the silicate structure of feldspar is tectosilicate, sorry, framework silicate, sorry. And the autoclase has a good cleavage. What is cleavage? Cleavage is suppose the mineral breaks. Okay, when it breaks, it will break along a smooth plane. You can see that when it breaks, the surface which is left behind is a smooth. So the this mineral has a good cleavage. Good, or there are other terms we use, that is perfect, there is imperfect, there is indistinct, and then there is absent. Okay. And fracture is any like suppose the crystal does get damaged, the mineral does get damaged. So the surface won't show a plane, but there will be a broken surface. Now these broken surface also show different kind of forms. Okay, so this is one of the identification factors even for these minerals. So this mineral has a conchoidal fracture. Okay, conchoidal means that have you ever seen a glass breaking? It forms like concentric circles. So that is called conchoidal fracture. So the name of this mineral is actually orthoclase, which is a potash feldspar. Okay, and it usually occurs in igneous rocks and sedimentary rocks. Most of the time, it occurs over there. So the next one, uh, can you guess? Can you tell me the color for this? What does this look like?
Greenish.
Yes. So this is green. And the luster is, any guess? Okay, so the luster, as you can see over here, is also vitreous. Then streak is also usually white for this mineral. Hardness is around 6.5. Then the crystal system, this is again another monoclinic mineral. Okay, so again you can see one of the axis will appear as if it's tilted. The mineral group diopside is a pyroxene. I'll just, yeah, yeah. So diopside is a pyroxene. So sorry, the hardness is between 5 to 6. Okay. Then crystal structure, as I had told before, so the pyroxene will be one of the inosilicates. So you have the inosilicate is the pyroxene is the single chain inosilicate. Okay, single chain the silicate structure. I will properly write these down, and then I will update the Google Slides. Also, I will share the links today for the recorded lectures and also the slides, so it will be easier for you all to follow. I'll explain that after the session is over, after I finish my presentation. Okay, so the cleavage for this would be it has a good cleavage. Okay, sorry, it has an imperfect cleavage because the cleavage, the plane is not very smooth. So that is why we are calling it imperfect. Okay. So, and it doesn't have a very visible, like very notable fracture as such. So we are not, I'm not explaining that over here. So this is a diopside. Okay, it's a pyroxene mineral, and this is again found in mostly igneous rocks. Okay, so can you all like tell me the color for this mineral?
I think yellow or golden.
Yeah, so this is a yellowish gold. Okay, So this luster is different. The luster that you can see, it is like a metal. So we call it a metallic luster. Okay. The streak. Now this looks yellowish golden, but this is not exactly. When you draw the streak for this, it will not appear yellow. Okay, it will appear black. Now this is due to its mineral composition, which I will tell now, like later on. So its hardness is somewhere around 6. So, and the crystal system, can you suggest? It's a very clear indication what the crystal system would be. It looks like a cube. So the crystal structure is cubic. Okay, the mineral group, this is a non-silicate mineral. This is actually, FeS, that is iron sulfide. Okay, so the iron sulfide is the sulfide group of minerals. Okay, since it's a non-silicate mineral, we don't have a silicate structure for it. The cleavage is also, a, it has a good cleavage, or actually these minerals are not very cleavage, you cannot see very clearly for these. Okay, so the name of this mineral is pyrite, and these usually occur in sedimentary rocks as sedimentary minerals. Okay. So these are some, like how I was saying, that each class, each crystal system will have different, forms, crystal forms. So these are different forms of a cubic crystal system itself. You can find pyrite in both these forms also, but the crystal system remains cubic for these. Okay. So the color for this is obviously it's transparent. Okay. The luster would be vitreous. This does not have a streak because its hardness is 7. Okay, any mineral that's whose hardness is above 6.5 will not show a streak. It will just show a scratch on the tile. Okay, the crystal system for this is hexagonal, actually also better known as a trigonal system. Okay, so the mineral group is it's silica. So it is SiO2. Okay, this is a silica mineral. So the crystal structure that we see for this is again a framework crystal silicate structure. Okay, this this is one example of a mineral which does not have a cleavage. Okay, the cleavage is absent for this mineral. And this shows the conchoidal fracture is very particular for this mineral. So we have conchoidal fracture. Okay, so the name, this is a very commonly found mineral, that is quartz. Okay, and this is one mineral which occurs in all of the types of rocks, like igneous, sedimentary, metamorphic. Okay, now we know that this quartz is transparent in color. This quartz is also called rock crystal. But you will also find quartz in different colors. Like rose quartz is pink, amethyst is purple, and smoky quartz has this brownish color. Okay. Now these colors happen because of inclusions in their silicate structures. Some ionic, inclusions happen where something is kind of one of the ions is substituted for another ion. Okay, that is when you find colors in quartz or even in other minerals for that matter, like sapphire, ruby. Okay, these two are actually from the corundum group. Okay, both are corundum, but they appear different in color just because of the impurities or the substitution that happens in their crystal structure. Ruby is, that's why, red corundum, and sapphire is a blue corundum. Okay. This is one example of a metamorphic mineral. Okay, this is a metamorphic mineral. So the color for this will be blue. The luster is, this mineral varies in its luster. It's is vitreous, as well as sometimes it shows pearly uh, luster. Okay. Its streak is present. It is around, I think, white. Mostly it is a white color streak. Okay. Now this is a unique mineral. This has two types of hardness. Okay. So if you rub this mineral along its long axis. Okay. Suppose the crystal is appearing like this. If you rub the streak along this axis, it will show you a streak. But if you rub it, perpendicular to the long axis, it will not show a color in the streak plate. Okay, so this has 5 in one direction and 7 in the other direction. Okay, so this has a dual hardness. So this belongs to the crystal system of triclinic. Triclinic, where all three axes are in different angles and different lengths. Okay. Mineral group, this is actually aluminium oxide. Okay. So this is an oxide mineral. So it has no silicate structure, and its cleavage is it's there, but it's not very it shows a good cleavage. Okay, just remember, it shows a good cleavage. And fracture, you can see that these are like blades. You can see these are blades. So these the fractures is these uneven kind of surface that you can see on the top. Okay, so this kind of fracture is sometimes called Hackley. So the name of this mineral is kyanite. Okay, and this usually occurs in metamorphic rocks. So same thing again. These are different ways kyanite is found. You can see that there's a green color here, and then this is again a blue and white combination. So now we see the different kinds of minerals. Now a same combination of minerals can be found in all the three different types of rocks. You can find quartz, feldspar and mica in granite, that is an igneous rock, in sandstone, that's a sedimentary rock, and also the gneiss, which is a metamorphic rock. So that is why identifying minerals is important, and also the way they occur, the association that they have, and identifying the rocks in a way, the how rocks appear and the texture that they show, that is important to identify and characterize the rocks. So if you all have gone through the lectures, you all have seen the different forms of intrusive rocks. Okay, so there is a dike and a sill. Okay, so can you all tell me which would be dike and which would be sill? Any idea? If have you all gone through the lectures? Okay, I'm guessing you all have not gone through the lectures. So the image to your right, to your left hand side is a dike. Okay, so this is a discordant form. Discordant meaning it's disrupting the the layers that are already present before this intrusion took place. Okay, these are forms of igneous rocks. So the igneous rocks are formed due to the extrusion of magma. Okay, so when the magma is extruded from the earth's surface, it is dissecting the already present horizontal layers. Okay, so it's disrupting, so it is called discordant. Okay, now over here you can see the black layer that is following the trend of the lower formation, or everything is horizontal. Okay, So this is conforming to all the pre-existing horizontal rock that is there. So this is called a concordant intrusive body, and this is a sill. Now these are forms of extrusive rocks. Okay, the left hand side ones, these are basalts. Okay, this is an example of Gilbert Hill from Mumbai, Maharashtra. Okay, these form a structure that is called columnar structure. Okay, so these are basalts and these are extrusive rocks. And over here you can see horizontal lines over here, the dark lines and the light lines. These are different lava flows. Okay, so lava flows and then it cools down. Then again again volcanic activity happens and again the lava flows on top and cools again. Okay, so this is an example from the Deccan Deccan volcanics, the basalts that we have across Maharashtra. So now we come to classification of igneous rocks. Classification can happen based on the magma origin, the mode of cooling, the grain size and the mineral composition. Okay, so magma origin, there are two types of magma. One is acidic and one is basic. The acidic has more silica and it is more viscous. Okay, so it accumulates in one place usually. So there are some forms which is called batholith. It is mentioned in the lectures that Sir has given. So batholiths are usually acidic magma forms batholiths. Okay, basic magma has it is silica poor. It does not have silica content a lot of it, and these are less viscous. So when we see volcanoes and we see those lava flows, the lava that is coming out, that is actually basic in nature. So that is why it can flow a larger distances. Okay. Now, acidic magma usually creates, lighter colored minerals, which together form lighter colored rocks. And for basic, they usually have, darker color minerals, and that is why they're called mafic rocks. Okay. Mode of cooling, if the magma has come out of the earth's surface in the form of lava and it's cooling down on the surface of the earth, it is an extrusive igneous rock. If the magma is cooling, inside the earth's surface, okay, and so it is called intrusive igneous rock. Now the grain size can differ with two respect. Okay, the mode of cooling and the rate of cooling. You can have an intrusive rock, but it can cool quickly and form finer grains. Okay, and you can also have an extrusive rock that has cooled over a longer period of time, and that is why the crystals are formed better. The crystal structure for each crystal, they take time and they cool in the proper crystal structures. Okay, so these will you can see these crystals in your naked eye in the hand specimen also. Okay, so these are then coarser grain, like you can see the mineral grains. Okay, so you can it depends on the rate of cooling also and also the mode of cooling of the rocks. So as according to the grain size, you have around, like if it's very big grains, like you can see it's 1 centimeter big grain, then it can be called a pegmatitic texture. These are textures. Okay, so pegmatitic texture. Then if they are visible, but they are not very big. Okay, then it is called phaneritic. And then if they are very fine grain, you can hardly distinguish, just by eye, like whether the minerals are present or not. Then it is called aphanitic. Okay, and then you have classification according to your mineral composition. Felsic rocks, okay, felsic rocks, light colored rocks usually have more of silica and very less or 0% of mafic. And on the other end of the spectrum, You have ultramafic rocks, okay, which have 0% silica and it's mostly made up of mafic minerals. So this is one example of a rock. So as per color index, this would be a light colored rock. So we can call it a felsic rock. Okay, color index size. The grain size, you can see the grains. Okay, you can see the grains. You can distinguish one grain from the other. So you would call this a pheneritic texture, or the grain, the texture based on the grain size. Now, if I say that the mineral composition for this is mostly made up of, silica rich minerals, okay? Silica rich minerals like, suppose I say it's quartz and feldspar and plagioclase feldspar and mica. Okay, so these four kinds of minerals have a lot of silica in their structure, in their composition. So then that is why we can say that a this is formed from the acidic magma, okay? And since you can see the grains, it is a phenolitic texture. So you can say that the rate of cooling was very low because the crystals took their time to form. Okay, they took their time to form. You can see the crystals. So you have acidic, felsic rock, and you have phenolitic texture. So this is most probably an intrusive rock. Okay, so intrusive rock. Now there is one particular kind of texture that is there. You can see there is a uh, there is kind of a big crystal over here which is surrounded by smaller mineral grains. Okay, this is one of the texture that is called porphyritic. Porphyritic is very usually seen in intrusive rocks and also some extrusive rocks, but that is a different kind. Some minerals which had already cooled before and then they got assimilated in the magma and then they cool down. So you can see porphyritic texture in such extrusive rocks also. Okay, so porphyritic texture is also kind of seen in this. So the name of this rock is granite. Okay, so the occurrences, it can occur as intrusive rocks and it mostly occurs in forms of batholiths and stalks. Okay, now as per the color index, you might say that it's a dark colored rock, but this is actually an intermediate rock because you can see that there is a mix of white and black mineral grains. So we'll call this an intermediate colored rock. Okay. Now the grain size is it's like over here you cannot see very clearly, but on this surface you can see some grains. Okay. So this is a kind of in between of pheneritic and aphanitic, but we can still see the grains. Okay. The mineral composition for this rock has, it has plagioclase feldspar, which is mostly sodium and calcium feldspars, and it has some amount of pyroxenes. Okay, like the mafic minerals. It has an equal quantity of silica-rich minerals and silica-poor minerals. So this has plagioclase and some mafic minerals. Okay. So the texture for this is, again we can say this is a pheneritic texture. We cannot see very clearly the mineral grains and there is no big grain surrounded by smaller grains, so we cannot even call it the porphyritic texture. So the name for this is dolerite. Now these rocks are usually found in the form of dikes and silts. Okay, so these are partly intrusive. They are formed in the by intrusive as intrusive rocks, but they are also cutting across different kinds of pre-existing rocks. That is why they are called dikes and silts. Now this rock Okay, so the color index we can see that it is mostly a dark colored, so we can call it a mafic rock. Okay, now grain size over here we can see that there are big grains. Okay, but these are not actually mineral grains. These are mineral precipitates which are accumulated within these kind of holes that you see. Okay, these are actually extrusive rocks. Okay, these are extrusive rocks, and when they were cooling, they had gas bubbles and they had, water content also in them. So these bubbles burst and the water evaporates later on, and then they leave these structures. Okay, so these, bubbles or these holes that we can see, these are actually called vesicles. Now, sometimes these vesicles later on, due to maybe the environment that these rocks are in, you have other secondary minerals that are precipitated into these, holes. So when these holes are normally called vesicles, but then when they are filled with a different kind of a mineral, they are called amygdales. Okay. So when we are considering the grain size, we do not consider these minerals. We only consider the the black parts. Now the black parts are very fine grain. You cannot distinguish the minerals. So we will call this uh, aphanitic texture. Okay. Aphanitic texture based on the grain size. The mineral composition over here we can say that these are mafic minerals. That is very low in silica. That is why your dark color comes to these rocks. Okay. So texture now, when there are vesicles present, there is a texture called vesicular texture. And if the vesicles are filled with secondary minerals, like you can have calcium carbonate in it, or you can have, some kind of silica precipitates also, then these are called amygdaloidal texture. Okay, so the name of this rock is actually basalt. So you usually find a lot of vesicular basalt and also amygdaloidal basalt. So these occur as lava flows, and the most common example that we all might be knowing is the Deccan province. Okay, so these are actually extrusive rocks. Okay. Now this color, while you might say that this is a light colored mineral, light colored rock because it has a light green shade, but actually this is an ultramafic rock. Ultramafic rock, why? Because this is essentially made up of olivine and pyroxene. Okay, so these are extremely mafic minerals. They are very low in silica. Okay, so that is why these rocks are called ultramafic rocks. Olivine is actually a green color mineral. Okay, and these rocks very characteristically show the presence of these olivines. That is why. Grain size, while you can see the above one is it could be a fine grain rock if you cannot see the mineral grains, but the lower one you can see the mineral grains. So it can be both aphanitic or phaneritic. Okay. So the mineral composition, as I said, is mostly it's 90% made up of olivine. Okay, when it's 90% made up of olivine, it is called dunite. When there is a mix of, olivine, pyroxene, amphiboles, sorry, not amphiboles, olivine and pyroxenes, it is called a peridotite. The lower one, the rock which is on the blue background, actually is a peridotite rock. Okay, it, the texture you can as I mentioned, it can be aphanitic, phaneritic, and it could sometimes have those porphyritic texture also. Over here we cannot see that, that is why. So this is a peridotite rock. Now, as if you remember the Bowen's reaction series, olivine is the first to crystallize out. Okay, so usually olivine is not easily seen on the Earth's surface. So that is why even peridotites are not very easily seen on the Earth's surface. Okay, so these actually crystallize at Earth, in ocean crust only. As we had discussed in the previous session, oceanic crust is denser because it is made up of mafic rocks, ultramafic rocks, and peridotite is also one of the constituents of the oceanic crust. So that is why these rocks are usually found in such areas. These don't get a lot of time to come to totally over the Earth's surface. Only when later on, due to collision, if the oceanic crust is lifted on top of the continental crust, we find the occurrences of these rocks. So now we come to the types of sedimentary rocks. You have three origins of it: detrital, chemical, organic. So detrital is like the pre-existing rocks. They are disintegrated. They form different rock fragments. They are then, carried to another place and deposited over there. Over there, like we can see, with weathering, rock fragments are formed. After weathering, accumulation at a place takes place. Then, due to either some tectonic processes or just due to the pressure of the consecutive accumulation of sediments, lithification or consolidation happens. Then we have a digenesis. Digenesis is what happens after the deposition of the sediments. Either compaction happens or cementation or recrystallization. Compaction is all the sediments are slowly compacted together. Okay, so they become a dense layer. Cementation is there are pores between these sediments. Okay, the pores are they act as ways for fluids to go between the pores, and they precipitate out as cements, and then they cement all the sediments together, and together then they form a sedimentary rock. And recrystallization happens, suppose there is immense pressure from any of the direction. It could be under stress or in that sort of a, environment. Then some of the crystals in the previous rocks, they recrystallize, and then when they recrystallize, they again accumulate together and form a rock. So this is the process of how sedimentary rocks form, and it can have detrital, chemical and organic origin. So now again, if we compare the rocks that are formed in the Bowen's reaction series, we can see actually the rocks which form first when the magma is cooling down are actually the first to weather. So they are highly unstable minerals when they are acted upon, by wind, water or glacier, like during weathering and erosion. And the last to form, that is the quartz, is also the last to weather away, as in disintegrate. So this is the most stable. That is why I said even before that quartz is commonly found in igneous as well as sedimentary rocks, because they don't get decomposed into another another mineral. They retain their crystal structure and chemical composition. So they are the most stable minerals. Again, this is a clastic sedimentary rocks. Clastic rocks are those rocks which, the sediments that are there in it are mainly rock fragments, prior existing rock fragments. The prior existing rock fragments can be igneous, sedimentary, or metamorphic. Okay, so when these rocks, due to weathering, disintegrate into different rock fragments, these rock fragments, when they undergo accumulation, lithification, diagenesis, they form clastic sedimentary rocks. So there are different kinds of sediment types, and these sediment types are actually based on their sizes. So you have gravel, sand, silt, clay. Now, as per the grain size, they are again, distinguished into different categories. Like in the gravel sediment type, you can have boulders, cobbles, pebbles, granules. And even in sand, you can have very coarse sand, medium grain sand, fine grain sand, or very fine grain sand. and anything less than 0.062 millimeter will be silt, and then lower than 0.004 millimeter in diameters. Okay, these are the diameters of the sediments. You have clay. Now, according to the grain sizes, you have the first classification, that is rudaceous. Rudaceous is usually a combination of gravel and sand, like not fully sand, but you will find some sand size particles also in rudaceous rocks. Arenaceous rocks is mostly made up of sand sized sediments, and argillaceous is silt and clay sized sediments. Then, due to we have classification on based on grain shape. Grain shape also, tells us how far the sediments have traveled before they got consolidated into the sedimentary rock. More angular they are, as in the surface of the sediments are very rough, we can say that these have not traveled very far. They just, traveled a little, and then they got compacted over there, and then they form the sedimentary rock. So there is a gradation. While the end member, well-rounded, is actually the it has traveled long distances, and after that they have got compacted. Usually, well-rounded sedimentary rocks, are those that are formed pretty far away from the weathering conditions. Suppose if we consider rivers bringing down the sediments, well-rounded sediments will be formed at around the mouth of the river, not at the foothill of the the mountain where the river was coming down in full force. Grain sorting means the amount of these angular sorry, grain sorting means the amount of different sediment types that are found. Okay, if you find gravel, sand, and silt, it is poorly sorted. But if you find only sand-sized sediments over there, then you can say that it is well sorted or very well sorted. Okay, so this is how we classify clastic sedimentary rocks. So, for example, over here, you can see that this rock, you can say that the sediment type is mostly gravel. Okay, so you see there is gravel size because you can see the sediments very clearly. Okay, so the grain size according to that would be somewhere between 256 mm to say around you know 4 mm. This is just rough estimate. We do not have the scale for this, so I'm just explaining how it might look like. So how will you classify it? So this is a rudaceous rock. Okay, so it's a rudaceous rock. Roundness, you can see that this is not well rounded, but you cannot see a lot of angular grains also. So you can say that these are, uh, it varies from subangular to, just rounded or sub-rounded if you wish. Sub-rounded, subangular to sub-rounded. Sorting, this is a very poorly sorted rocks because we can see different kinds of grain sizes and also different kinds of sediments over here. You can see a big boulder, you can see some pebbles, some cobbles. So that is why this is a poorly sorted rock. The name of the rock is conglomerate. Usually conglomerates are found in this form only. Okay. Now over here sediment type, you can see that these are also mostly made up of gravel, and you have some cobbles, and okay, and you have some granules. Then the grain size over here is again some mostly between 256 to 4 millimeter probably. Then the classification for this is again rudaceous. Cretaceous, and then the roundedness, these are angular. You can see very clearly that they are, geometric shapes. They are not rounded, so you can just, call the roundedness as angular grains. And this is again poorly sorted because you can see different, kinds of sediments and also the sizes. So this is a poorly sorted rock, and this is called a breccia. This is another sedimentary rock. Okay. Now over here we can see that mostly right now, since the scale is not here, so it's not very clear, but these are sand sized grains. Okay, so these are sand sized grains. So the grain size will fall somewhere between 2 to say 0.5 millimeter. Okay, so this means that these are, this is a, you can say, medium grain. Okay, medium grain sized, medium sand sized sediments are there. Roundedness, you can see that these sand over here is, it it is not very well rounded, but it is not very angular also. So you can call this a sub-rounded, grains. Sorting, you can see that all of these are sand and all of these have similar sizes. So you can call this a well sorted. Okay, and this is a sandstone, a very commonly found sedimentary rock. The Red Fort is one of the monuments that is made up of this rock. So hopefully, you can remember this rock by in that with that association. And over here we can see that you cannot make out the sediments, the different sediments or or the size of the sediments. So these are actually the sized, so silt sized or clay sized sediments are present. The grain size is again, it's obviously it is less than 0.062 mm. Okay, because you cannot see it with the naked eye. Then the classification is actually argillaceous. Sorry, I forgot to classify this one. This is actually arenaceous. Okay, so the roundness, since you cannot see, so it's not, it's not very visible, so you cannot say much about it. Sorting, you can say that since this is made up of, silt and clay sized sediments only, you can say that this is a well sorted rock, and this is actually a shale. So this is how, you identify first the properties of the rocks, okay, and then you see the chemical composition of it. Like if you can identify just with the properties, like how in igneous rocks we saw that a light colored rock is mostly a felsic silicate minerals. Okay, so that can be quartz or feldspars or mica. So this is how we kind of identify the rocks. And again, identification of rocks is important to understand whether they have hard minerals or soft minerals. Any rock which constitutes of soft minerals is not very, it is not favorable for, construction purposes. So like sandstone, you can see is well sorted. Okay, and it is mostly made up of quartz and feldspars, which are comparatively very stable minerals. Okay, so sandstone, we know that it will not weather very easily, as in it will not get eroded with easily, it will not get disintegrated very easily. So you can use a sandstone in your construction. The similar thing goes for granite. Granite is also used for a lot of constructions, and later on we will see some metamorphic rocks also that you can use for construction. So if you have any questions regarding this session, whatever I have taught, or any of the lecture material, you can ask now. I'll also copy paste. I'll give the links for all the resources.
Yes, ma'am. Please share this link for this today's lecture.
Okay, so I have shared the links. So the first is the feedback or the question form. You can send, you can, put your questions or any kind of suggestions that you have or feedback for this session. The Google Slides link that is there, that I will update every time after the lecture is done. Okay, so you can get those over there, and the YouTube channel is there. So there you can you will find the recorded lecture mostly. You will find it either by tonight or tomorrow morning. So you can watch these again, and if you have any doubts or anything, you can use a question form, or you can use a discussion forum also, and you can ask your questions there. I just wait a minute. I'll stop the recording here.